Well, heidi ho there, neighbor. This is Unit 6, Lesson 1, AP Calculus AB. We are going to be going over antiderivatives and slope fields. We've been doing some antiderivatives already, so this is kind of like a reinforcement thing. The slope fields will be new. So let us get started. All right. So first, a little review. Let's consider two equations. We have y equals x squared plus 3, and we have y equals x squared minus 5. All right. So if I wanted to find the derivative of each one of these, okay, first off, I hope you know that the derivative of x squared plus 3 is just 2x. All right. So let's go over here to the right a little bit. And if I take the derivative of x squared minus 5, I should note that is also 2x. So does it really matter what our constant was in the original equation? I mean, does this really matter? Because ultimately, we end up, when we take the derivative, the same thing. It ends up being 2x, all right? However, we have this thing called integration, okay, where we do the reverse operation, all right? So now they want us to find y. All right, well, my rules of integration tell me if I have the derivative and I want the original equation, I integrate 2x dx. I take 2x, I add 1 to my exponent, that becomes a 2, and whatever that sum is, I divide by that. My 2's cancel. I get x squared. Okay, so if I go backwards from 2x, I get x squared. But this statement ties in to what we just did. We don't know what the constant was. Was it 3? Was it -5? Whatever. So we put a c in the answer to remind us that there might have been a constant here. So my answer isn't just x squared, it's x squared plus c. Okay? And let me revert back to the previous slide. If I go backward from 2x, how do I know if I went backward from this 2x, it was 2x plus 3? If I went backward from this 2x, it's 2x minus 5. Okay? So what we're trying to say here is, if we go backward from this 2x and integrate, well, how do I know if it was -3 plus 5? Maybe it was just x squared. Maybe it was plus 0. Okay? Meaning, I could have had x squared plus 3 and ended up with 2x. I could have had x squared minus 5 and ended up with 2x. I could have had x squared, which is technically plus 0, and ended the same thing. So when we integrate, we don't know what that constant is. It could have been any one of these things here. So what we do here is we just put a plus c, letting us know, hey, there was a constant, but we took the derivative of it and it went away. Yes, maybe that constant was 0, I don't know. But maybe it was +3. Maybe it was -5. We just don't know. That's why we put a plus c there. Maybe if we had some more information, we could actually find out what that c is. Maybe we could find out, hey, it was really x squared plus 3. No, it was really x squared minus 5. Maybe it was x squared plus 13. I don't know. But if we had a little bit more information, we could figure this out. Enter initial values, okay? Now, they give us this problem. They say, okay, y prime, or my derivative, is 2x. And they want us to ultimately find the equation for y, which means I need to integrate to find my original equation. But they give us this new information right here, okay? Y was 4 and x is 1, okay? So given y prime equals 2x and y equals 4 when x equals 1, this is referring to our original equation, we'll find that y, our original equation, okay? This is called an initial value problem. We need the initial values to find our constant. We need more information than just, oh, integrate this. We just integrated 2x dx. We came up with x squared plus c. That was my original equation. The original equation might have had a constant here. We don't know, so we just put plus c. But now when they give us slightly more information about our original equation, they give us initial values, and we call these things initial value problems. An equation containing a derivative is called a differential equation. Derivatives, differentials, differentiation, it's all the same thing, slope, okay? It becomes an initial value problem when you are given initial conditions and asked to find the original equation. So we found y. We don't know what c is, but now they give us a couple of pieces of information. When y is 4, oops, sorry. When y is 4, x is 1. Now I can definitely find out what c is. Okay, let's do that. So I have 4 equals 1 squared is 1 plus c. Therefore, c is 3. It's a positive 3. Okay, I hope you know that 3 plus 1 is 4. Now I know c. Guess what? Y equals x squared plus, this was c we had here. But now we know c is a positive 3. And this is the exact original equation that my derivative came from, given my initial condition where y was 4 and x was 1. Okay? Slope fields. Awesome. And by awesome, I mean not awesome. They're not difficult. They're you got to be patient. You got to go through it very carefully. Make sure you don't make a quick mistake because it's a lot of simple algebra. So don't make any mistakes by going too fast. Take your time. All right. Initial value problems and differential equations can be illustrated. That can be illustrated. They can be displayed with picture by using a slope field. Now, slope fields are mostly used as a learning tool, and they're mostly done on a computer or graphing calculator. But on a recent AP test, and I mean on any AP test, the test asks students to draw a simple one by hand. Okay, and they are not that difficult. We'll start doing these things, and you'll realize they're not that difficult. They're just tedious. It's like geometry teachers and proofs. Okay, most teachers who've either taught geometry a couple times or have taught geometry their whole life really aren't crazy about proofs. Okay, some of them are. Hey, we got some nuts out there. Hey, God bless them, love them. Okay, they're dedicated to that content area, let me tell you. But I taught geometry before, and I really just don't like proofs. Okay, everything else is cool in geometry, but proofs, I'm like, yeah. Slope fields falls under the same category for me. I mean, they're fine. I could do them. They're great. I like taking the derivative. I like taking the integral. I like putting these in real life situations. But slope fields are kind of just, they're there for the purpose of doing math, in my opinion. But they do have a purpose behind them. We'll get into that maybe another time. Okay, let's take a look at an example of a slope field. Okay, we've been using y prime equals 2x. We've had a derivative of 2x as an example for everything we've done so far. So let's keep on using that, shall we? Here's what the slope field for y prime equals 2x looks like. Now keep in mind, slope is the same thing as derivative, okay? So if my derivative is 2x, this is what my slope field looks like. It is a series of straight lines at coordinates that represent the slope at that coordinate. Let me say that again. And let me scroll down here, right? Each one of these lines, okay, each one of these lines, no matter where you look, represents the slope right at that coordinate, okay? Every one of these lines represents a slope at that coordinate. If the slope is 2x, okay, and I know what the x value is, I can just plug the x value into 2x, and that tells me the numeric value of the slope. So let's take a look at this table we have to the right. If my slope is 2x, at the coordinate, which is the origin, 0, 0, Isn't my x value 0? Well, I just plug a 0 in here. 2 times 0 is 0, and that's my slope. That's a horizontal line. So at the origin, I'll do this in red. At the origin, which is right here, I have a slope of 0. Okay. Let's look at this point right here, which is 1, 0, which is this right here. My slope is still 2x. What's my x value in this coordinate? It's 1. So I plug that in for my x. 2 times 1 is 2. So at my coordinate, 1, 0, my slope is 2. So there you go. That's a positive slope. Let's look at this one. We'll do one more. That's the coordinate 2, 0. And we'll do this yellow. Hopefully this comes out good. 2, 0. My x value is 2. So I throw a 2 in for my x. 2 times 2 is 4. My slope is 4 at this point. So that is steeper than 2, which is obviously steeper than 0. Okay? And that's all we do at each one of these things. At each one of these coordinates, that's all we're doing. Okay? Now, you might say to yourself, how come in this table I need a y value? The y value has nothing to do with my derivative here. Well, sometimes the derivative might be 2x plus y. Now I need an x and a y. Okay? If this is my x, 2, and my y is 0, I would throw a 2 in here plus a 0. Okay? Or 1, 1, I would throw a 1 in here and then add 1 to it. Okay? So sometimes the y is in there. Okay? And also, how come we need the y? Well, I need to know what the coordinate is where the line goes. If I have the x value, I also need the y value for the coordinate. Okay? If I just had an x value of 3, that's a vertical line at x equals 3. That's not a point. I need the y value to make it a coordinate. Okay? Got to coordinate, children. All right. So I think I've kind of given you a decent enough explanation of so that you kind of know what a slope field is. And really, the best way to start understanding slope fields more and more is to just do them. It's just algebra and just, you know, drawing a straight line to represent the slope at every one of these points on the table. Okay? So let's move forward, shall we? Okay. So this is still our example. Let's bring initial conditions into this. All right, let's bring initial conditions into this. Meaning, if I go back, I'm just going to draw on this previous one here. If I pick any area here, let's say right here, I follow the slope. It kind of goes down, then it gets less steep, then it kind of comes up, then it flattens out right here, then it goes up, then it goes up even more. That's obviously a parabola. But my graph doesn't take up the whole axis every point like it does here. It would be a parabola here, maybe the parabola is here, maybe the parabola is here. I don't know, but it's somewhere it's a parabola, okay? It's a parabola somewhere. Okay, if I follow this. I could pinpoint more exactly where that parabola is if I know an initial condition, such as 1, negative 2. So if I look at this point right here, okay, and I plot this, I don't know, here's 1, here's negative 2, so it's somewhere around here, right? Big dot right there, boy. Okay. Now, if I know that my graph has to go through that point, well, okay, it kind of comes down, goes through this point, flattens out, comes back up. My parabola should be exactly right there because I know the point. It's not up, down anymore. If I touch this, it fades out. Okay. That's exactly what I have. Okay. That's exactly what I have. Look at that one, right through the point. Look at me. I just made this wider. I'm so terrible. I'm a terrible person. Anyways, cut. Right, there you go. I know exactly where that is. There's no doubt in my mind that parabola, the vertex, isn't above the x-axis because it has to go through that point that's below right there at 2, 1, and then follow how the slope goes, all right? Now, by following the slope field, you get a rough picture of what the curve looks like. In this case, it's a parabola, okay? The piece de la résistance. What if we have to draw a slope field? This is what we've been building to right now, okay? My dy dx, which stands for derivative, which is the same thing as slope, is 3x plus y. I am going to put the slope field. I'm going to draw lines that represent the slope at the coordinates everywhere where there's a black dot. Okay, notice on the y-axis there are no black dots, so I don't care about that. Only where the black dots are. So the first thing I'm going to do is I'm going to make a table. Here's my x's, here's my y's, and then here's my slope. Okay, that's dy dx, and that equals 3x plus y. Okay, go all the way down like this, all the way down like this, and we'll go over once because we can. Now I see 9 dots here, okay? I'm going to start with -1. See, there's -1, 0, -1, 1, -1, 2. So -1, 0, -1, 1, -1, 2. And do the same thing for ones, okay? 1, 0, 1, 1, 1, 2. I do the same thing for when my x is 2. 2, 0, 2, 1, 2, 2. Okay, now I'm just going to get rid of these like green little dots I made here. And now, given these x's and y's, I'm going to find the derivative for each one of those points. Okay, for each one of those points. All right. So when x is -1, and I want to do, you don't have to really, this is mental math that we can do. So I'm going to show you the first couple, actually plugging them in. But this is really mental math that you should be able to just rip right through. I have 3 times my x value, which is -1, plus my y value, which is 0. And that should give me -3. Okay. Now, I'm not going to draw that now. I like just finishing the table. Then my reward is to do no more math and just draw and color. That's my little reward to myself. Okay. So the next one, okay, it's 3. My x value is still -1. Now it's plus a y value of 1 because I'm using this set of coordinates right here. And I should get -3 plus 1, which is -2. All right. Now I'm just going to go through this quickly now. -3 plus 2, this should be -1. All right. Now I'm going to do the ones. If I throw in a 1 for x, it's 3 plus a y, 0. That's 3. This would be 4. This would be 5. Okay. Now I'm going to do my 2's and their coordinates. Okay. That's going to be 6, 7, and 8. Okay. So you're going to see, you can literally see my slope gets steeper and steeper as I go. So let me go ahead and plot these points, right? Or these, excuse me, put these slopes on the coordinates, on the points. So at my coordinate -1, 0, which is right here, it has a slope of -3. So I don't know, maybe it looks like that. At -1, 1, it has a slope -2. Now it's still negative, but it's not quite as steep. At this next coordinate, -1, 2, it's a slope of -1, and it's even less steep, okay? And it's still negative. Now, let's go to where x is 1. I'm going to put these slopes here, 3, 4, and 5. So now, and you'll notice as I go down, whatever I make my slope is 3, it should get steeper and steeper and steeper as I go. So 1, 0 has a slope of 3. 4, steeper. 5, steeper. 6, steeper. 7, steeper. 8, steeper. Okay, as long as it kind of gradually gets steeper, you're going to be okay. No one's going to take a ruler and measure these things. There has to be some common sense involved. First of all, if I wanted to start at -3 slope right here, it shouldn't look like that flat or like that. I mean, it should be kind of like this. And then, you know, you adjust accordingly, okay? You just adjust accordingly. I mean, we're smart enough to know what the heck a slope looks like. But in a nutshell, that's it. That's it. You've just done, and on a test, they just ask students to do this. I mean, it's easy, but I like taking derivatives and finding derivatives myself, like I said. So you kind of understand my feeling about this. But it is not difficult at all. The one thing you need to make sure you do, because everybody who makes a mistake, it's the simple math. You start ripping through this quickly, and you make simple mistakes. So take your time, do your algebra, and you'll be fine. All right. Before we end, all right, I want to come back to integrations. And there are two types of integrations. There's an indefinite integration and a definite integration, okay? The definite integration on the right here gives us these upper and lower bounds, all right? The indefinite doesn't give us any. Okay, I'm not putting a 0 there. I'm just highlighting that there are no bounds, okay? And you'll see up top here, it says to see or not to see. There's a little audio thing I press here, and there's some guy who says to see or not to see, and it's all fine and dandy, but the audio that's recording is on my mic, not from the computer output audio, so you wouldn't hear it. You're missing out on so much, really. You really are. So let's integrate x squared on both of these, okay? Let's integrate x squared. Now, x squared, I take my x, I add 1, that turns into 3. And whatever that sum is, it happens to be 3, I divide by it. So I end up with x cubed over 3. I don't know the original equation, so I have to put a c here, okay? This is my integration. I can say y equals whatever. Right there. Let's do the definite integration. The integral with bounds here. I still integrate x squared and I still get x cubed over 3. However, I have bounds. I want that value from 4 to 1. I do not put a c here. Those are not initial conditions. That's saying I want, remember, an integral is the area under the curve. Okay? Here, like, at what point? You want the area under the curve from where? I don't know. I just know I can use x cubed plus 3 to get there. And then there's some constant that I could use to find my equation, but I don't know what it is. If it's indefinite, this is where, yes, I put a plus c. For definite, no. There is no plus c. Don't look at that as a double negative and say, oh, that means no and no is yes. No, exclamation point. There is no plus c. Let me clarify that. You do not put plus c here because now you know you want that area under the curve from when x is 4 to when x is 1. So all I do here is I plug in 4 first. I literally plug 4 into my equation. And I get 4 cubed. I'm throwing a 4 into this x over 3. And I subtract. Plugging my bottom or my lower bound in. Okay? For x. 1 cubed over 3. That's it. I just want a difference there. I plug in my upper bound first. And I plug in my lower bound, and I subtract them too, okay? Find the values separately, then subtract them, okay? 4 cubed is 64 over 3, minus 1 cubed is 1 over 60. Yeah, 1 over 3. I almost went ahead and gave you the answer, okay? So 4 cubed is 64 over 3, minus 1 cubed, which is 1 over 3, and you get 63 over 3, which divides evenly to be 21. And that, my friends, is the end of today's lesson. Pip, pip, cheerio, good day, and I will see you for lesson 2 for Unit 6. I hope so. It was fun. It's fun hanging with you. See you then. Bye.